Swayam Prabha. Digital India. Educated India.
Now I'm going to come to the second topic about 2-degree freedom vibration and 2-degree freedom wave energy converter, right? So far we said with this buoy on the surface, right? Sometime we need to understand, let me tell you this system. I give you motivation first, right? So by now we fix this on the seabed, this move up and down, right? Sometime when you do experiment, you clamp on this bridge, then you have buoy move up and down. This is single body case. We have understanding on that. And we also say for this one to achieve resonance is not easy, right? And you need 8 to 132 meters bore, right, buoy, right? Or you have to take advantage of added mass and take advantage of rotation inertia, this type of thing, create resonance. And for this one, is 2-body system. One body on the water, another body submerged into the water. So now we are going to understand the 2-body system, right? So the outline the talk is modeling 2-degree freedom system. And we try to understand what the solution to the 2-degree freedom vibration system. Then transfer function. After that, we are going to talk about 2-body wave energy converter. Then how to optimize the parameter. Okay, so there are a little bit mess. Some of the equation you can read the slides. I will skip that. Okay, so I want to highlight physics, highlight some real life. Okay, so and still we use the potential flow, right? We need to understand all the system 3 unique things: added mass, frequency dependent; radiation damping, frequency dependent; and excitation force, frequency dependent. Okay. So this is slides we already showed you before, how to calculate the 3 frequency dependent parameter. Keep in mind, this is frequency dependent 3 parameter are related, right? If a system is symmetric, the water is deep enough, 1 parameter, from 1 parameter you can calculate the other parameter. Okay. Otherwise, you can use the software to do this calculation. Okay. So that is the single body case I mentioned to you, and this is 2-body case I told you already. This 2-body case too, right? You have this buoy, you have another plate, heavy plate, and this heavy plate, what kind of thing in your mind you are thinking? Is you can think that way. There's a big ball, right? This is added mass, right? This plate, there are also will have a lot of damping effect too, right? So because of shape, right? So radiation damping too and viscous damping. If the flow goes through clearly, the fluid will separate, right? Viscosity and drag damping will be large. For this one, this 2-body system, but the shape is slightly better. So in that way, you can think you are going to have added mass, you are going to have physical mass. In addition to that, the flow streamline shape better. For this one, this is 60-degree freedom system. This one will guide that. This only give head motion. This one you have pitch motion, yaw motion, or this 6-degree freedom system. So now, this vibration, typical vibration system, right? You have spring mass damper, this link in between, right? This is 2-degree freedom vibration system. 2-degree freedom vibration system, each mass, you take it out, you draw a free body diagram. For example, you draw this one free body diagram, this is the force, excitation force. Then the spring force, this K times the relative displacement. Similarly, you can draw the free body diagram. After that, you use Newton's law to write the motion equation, right? This mass, stiffness, right? So this excitation force. So for such kind of 2D freedom vibration system, and you can write in matrix form, right? This is mass matrix time x1 double dot x2 double dot. This is you time that you say is m1 times x1 double dot is this part, right? Then similarly you have stiffness matrix, right? This is k1 plus k2 times x1 minus k2 x2. It's just exactly this equation, right? This is 2D freedom system in matrix form, right? Now we talk about free vibration. Free vibration means you don't have excitation, right? The left side you have cerebral mass, right side you don't have force. So this is a 2D freedom system. There are two equations of motion, right? And you will say two natural frequencies, right? What's the natural frequency? Natural frequency we say square root k divided by m, right? So is this one or no? If you have two different systems, right? K1 M1, K2 M2. No, right? It's not like that. So it's for free vibration system like that. You assume that it takes this shape. You vibrate at the first frequency like j omega, right? And you have amplitude relationship. X is a vector, x1, x2. You have u is a vector, u1, u2, right? So you assume you take this shape and you plug this x double dot into this equation here. Now you have j omega t. You know j omega t is not always 0, right? 0 is trivial. So you take this j omega t out. You can write it in that way, right? The matrix times a vector, right? That is a characteristic equation, right? And to do that, and you have determined this coefficient to be 0, right? And you solve this determine this to be 0. This is a characteristic equation. This equation like this one. So further you have omega power 4, omega power 2, and you can solve this equation, right? So this equation you have omega 1 square, omega 2 square, right? So you can have fourth order system, you have four solution, right? And the fourth solution plus minus omega 1 plus minus omega 2. Okay. So this is one numeric example, right? This is 9 kilogram, 1 kilogram, 24 and 3 Newton, right? You saw that your first natural frequency is square root 2. Second natural frequency is 2, right? That is called natural frequency. This is you have two natural frequencies like that. Keep in mind the two natural frequencies you saw from the coupled system. So then after that, what's the u vector mean, right? You have two natural frequencies, omega 1, omega 2. U is a vector, right? What's the u vector? We called model shape. Okay. So for each value of omega, you plug this equation here. You can find one vector, right? For example, for this case study, you plug this number here. You can have vector take this shape, right? This is u11, u12, u11, u12, right? Vector you can have. You choose. Let us say the first one. No, second one u12 as 1, and this relationship you get u11. This vector, right? And what does it mean? Okay, I will tell you what that mean very quickly. Okay. And similarly, you have omega 2 here. You address that. You solve this vector, right? This negative 1/3 1. This is eigenvalue, eigenvector, right? Mathematically, you understand the eigenvalue, eigenvector. Okay, so let me say that way. Eigenvalue, eigenvector. I have u1 here, I have u2 here. Can I times this by 3? This become 1 and 3. Yes or no? Yes, why? Scaling is still hold here, right? So vector, direction, and amplitude vector, right? So for this eigenvector, eigenvalue, eigenvector, the direction matters, right? The amplitude can scale up, scale down. Okay. So what's the physical meaning? Okay, and this system, this called nature frequency, that called a model shape. What does model shape mean? Okay, so let me see. I want to show one figure first. Okay, and here model shape and frequency was mean. Okay, look at this one. The system vibrate at square root 2 frequency, and the shape is where x1, x2 be in phase, right? x1 more 1/3, x2 more 1. So this is the relationship. The shape always hold, right? So this is look like one single degree freedom system. The two always more in phase, right? This is more 1, this is more 3. Okay, it happened at natural frequency square root 2. Okay, another thing is, you look at here. This is negative 1/3. That means this two more to here, and then more to here, right? x1 more to negative 1/3, x2 more to 1. So we call out phase motion, right? One's in phase, another out phase. Another is amplitude ratio, that is negative 1, 3. So this means model shape. You can set up system vibrate, look like a single degree freedom system, right? The only thing is in the model space, model shape. So come here like that way. So if you have arbitrary input, right, and the arbitrary initial condition, you can solve that, right? Or overall is a combination of the first natural frequency and coefficients and second natural frequency coefficients, right? You have this I, B, C, D. This can be arbitrary constant. It's not really arbitrary, right? You have to satisfy the initial condition, right? Therefore, after you satisfy the initial condition, you find this I, B, C, D. Okay, so overall, the vibration system, you can write in that way. Okay, so let me go a little bit. Okay, so you apply here and use a Euler formula. Euler formula Ej omega t equal cosine omega t plus J sine omega t, right? Using such a kind of Euler formula, this expression you can write in that way. Okay, so that part is natural frequency, omega 1, omega 2. This vector is model shape, right? This shape. So then this I1, I2 is amplitude and phase. So that is how we understand 2D freedom vibration system. So I go through a little bit quicker. Okay, there are some mathematical equation I highlight physics. So that means how it vibrate is a combination of these two 1 degree freedom system. One is omega 1, one is omega 2. But the shape is U1, U2. One is like here, 1, 3, negative 1, 3. Okay. So this is physical explanation. Okay, look like two mass system look like a two vibration system combination. That is, each combination is just a motor shape. Okay, so one very unique 2D freedom system I want to let you guys know here. I talk about here tuned mass damper. Okay, and tuned mass damper is very useful vibration reduction device, and especially civil engineering. Let me show you some video before we continue. Okay, and that is YouTube system. Okay, this is just a structure here, right? Here this is another mass. At the beginning, this mass you can say it's locked, right? This more together. Okay, now they're going to remove that part. This is free to move. This vibration quickly reduced, right? So you can say significant difference. Okay, so that is a 2D freedom system, two mass, right? You can say one mass can quickly reduce the vibration of another mass. Okay, this is one specific 2D freedom system. Okay, so for the 2D freedom system, you write the matrix, mass matrix, stiffness matrix, damping matrix, right? So then you have force excitation act on the first mass. So you can find the solution if X takes this shape, this amplitude of primary system and observer system. So now that's the characteristic equation. So determine equal 0, you can find the natural frequency, right? And here, if you give force input, right, that is response, primary system, observer system, right? Now you simplify this relationship from here, you get X amplitude primary system and mass of amplitude of secondary system, right? This just take matrix form, okay, and this, when you solve that, and you have so-called damped natural frequency, right? Characteristic equation for this one, you have damping here. This is called damped natural frequency. Without damping is undamped natural frequency. Okay. So, and this amplitude transfer, you give the force excitation, right? You want to say amplitude. Okay, the amplitude, you have this relationship here. This one is primary damping. Okay, and then primary stiffness. Oh, let me see which one is primary. Am I okay? Not this CI is damping, is not primary damping. Primary damping is C. Okay, this is observer damping. What I said just wrong. Okay, the observer damping, this is the observer stiffness and observer mass, right? So let us see one special case. One special case, the observer damping is 0, right? If observer damping 0, as the excitation frequency, if the excitation frequency is same as the observer's natural frequency, the X amplitude will be 0. That means you have force excitation to the system, then the primary system, there's no vibration, right? You to completely kill the vibration, use one small mass. Okay, so that is vibration observer, we call it dynamic vibration observer or tuned mass damper. Okay, when it first come up, that was patented in 1911. Okay, and in that time, Deng Hartog and his co-author write one paper how to tune the system. Okay, so such kind of system has been used for different structure, like the Taipei 101. There are 600 tons or 660 tons of mass there, right? The U to reduce the vibration of the building. if the wind excites at that frequency, this building there's no vibration, right? In Taiwan, there are not all typhoon happen, and when this wind, small wind happen, this building is safe. Okay, because the vibration. Okay, so such kind of thing can be also used to reduce the platform vibration of offshore wind structure. For example, like an offshore wind platform. So we have one project work on the offshore wind platform. The idea here is to tune the mass damper here to reduce the vibration. Actually, it's not tuned mass damper, it's tuned inertial damper. What does that mean? We not only use this mass, we also use rotation inertia. That means in this system, we have two functions. One function is harvest energy. We put a rotation inertia, we put a generator here. When this mass are move up and down, we change this energy into electricity, right? We harvest energy from ocean wave. Meanwhile, it acts as tuned inertial damper. We reduce the vibration. And let me tell you how the tuned inertial damper work. So you have this move up and down, this drive a box screw, right? Box screw drive a generator. And then instead of just using this damper, we can use the damper and the inerter connected together, right? Then that will have effect as tuned inertial damper beyond tuned mass damper. What's the advantage? Advantage is we can reduce mass need. I told you, right? This one is 660 tons mass. It's a huge mass, right? And for floating wind, and its 5 megawatts is 13,000 tons mass, right? You reduce if you put a 1% mass there. What's that? 13,000 tons. 1% is still 13,000 tons. Okay, is 130 tons mass, right? You reduce the mass a little bit, is significant save. Okay, and anyway, if you guys Google tuned inertial damper, you will find some concept of what I mean tuned inertial damper. So here is mass, right? Another concept is the inerter. Inerter is force equal relative motion, the relative acceleration, right? So you have both screw and you draw that, you have relative motion. Relative motion generates force that is proportional to the rotation inertia. You both screw both ends, you move nuts and screw you move at the same time, there's no rotation, right? The physical mass is small. However, if you have rotation inertia like that, that's called inerter. Okay. Anyway, so this is wave energy class, and I'm not going to focus too much on that. However, it's also marine energy class. I want to let you know such kind of concept in civil structure can be used for for marine energy too. Okay, so I told you this is the case when CA equals 0 and primary damping is 0, right? And primary damping doesn't need to be 0, right? And you can have different damping effect. So overall, you can normalize the system using the mass ratio, normalized nature frequency, right? Normalized tuning ratio, right? The tuning ratio. Okay, primary system tuning frequency and absorber tuning. So overall, the transfer function you can write in that way. That's normalized frequency. Okay, so if you have system, primary system, that's damping, not primary system, this zeta is secondary damping, is this damping here. Okay, if you don't have damping, as I told you, you can almost kill the vibration at exactly the nature frequency of the overall system. Okay, now you will find, wow, you have two huge peak, right? This frequency you carry the vibration, but on other frequency you get huge vibration. This is less an idea, right? Therefore, you increase this damping. So, for example, you increase the damping for this case study from 0.01 to 0.4, you have this result, right? You can say, oh, well, we don't have risk of the two peak, but here the performance is not good, right? There's optimal damping. So optimal damping is trade-off. You try to reduce both peak and without increase vibration in the middle. So this is Deng Hartog's tuning rule. He published a paper in 1946. So this fixed point damping, a fixed point, that means you change the damping ratio. You find that these 2 points are fixed, always like that. And then he developed one way how to minimize the 2 points. So this is Deng Hartog's tuning. Okay. Now we are going to talk about more exciting work about wave energy converter, two-degree freedom wave energy converter. Okay. Which one is better?
So this tuned mass damping, can we have opposite effect? Small mass keeping, vibration increasing.
You mean opposite direction, small
Yes,
mass?
we are damping.
Okay.
Putting another mass, we are damping. The reverse possible. We can increase.
Small mass can increase the vibration too. Or you can say that way, right? Like when damping is small at this frequency, will increase the vibration. Right? Here in the middle part, you reduce that. Okay. So depend on excitation frequency, right? Just like this case, if you look at the transfer function A0, right? This primary, this is A, okay, absorber mass damping. If this is 0, you can make the excitation frequency, you can make the vibration amplitude to be 0 at exactly one frequency. So I show you that structure already, right? And now you put another mass, you reduce the vibration, right? So your question is, what's the meaning of one peak or two peaks? We don't count one peak, two peaks, that is one frequency. And you say one frequency here, you can make this amplitude almost 0, right? However, outside this, there are large amplitude. When you have large amplitude, you want to reduce the amplitude, right? Now you use this damper to reduce this amplitude. So you gradually increase the damper. If the damping is 0, you know this peak is high. If damping is infinity, what will happen? Look like single mass case. It's the original system, right? Such kind of mass usually small. You just one peak, then one peak at this frequency you have large vibration amplitude. So there's best damping here, right? The best damping is published, discovered by Deng Hartog in 1946. I didn't write the equation here. This closed form solution about how to tune this damping. Also how to tune this mass. This is why the tuned mass damper, you need to tune to exactly one frequency. Okay, so and such kind of phenomenon can be used for the offshore structure and wind energy control. Now let us come back to we understand the two-degree freedom system. Now let us say how to harvest energy from ocean, right? So this is a single mass case. right? And you fix to the seabed. Indian Ocean is very deep, average kilometer, right? You cannot build a kilometer column to fix to this seabed. Now, okay, I put another system, right? I have buoy here, I have another tank. Now it's two different system. Yeah, you can say, yeah, from installation perspective, yeah, I don't need another, I don't need to connect the seabed. Clearly, right side is better, right? How about performance? Okay, you guys already learned the added mass and radiation damping, the vibration system. Now, you can model the system like that way, right? So, for this one, and let me say that way, you have physical mass, you have second physical mass, right? So, first one you have radiation damping, second one you have radiation damping. Okay, first one you may have viscous damping, right? And second one you may have viscous damping too. Okay, and here you may have PTO damping, PTO stiffness. Okay, and you may have excitation force, right? Depending on how deep, right? If the wave amplitude becomes smaller, but you still have force on the system. So, as I mentioned that if system on the surface and normally viscous damping is small, right? Therefore, actually this is radiation damping. This one what I said just wrong. Okay, this is radiation damping. This is also radiation damping. Here, this viscous damping. Here we didn't put viscous damping here. The reason is the viscous damping compared with radiation damping is small on the surface. Okay, below the surface submerged into the water, and viscous damping and the radiation damping almost same. This is why here we equal viscous damping. Here we didn't with equal viscous damping. So something is still missing. We didn't draw here. Who can point out something? Okay, motion force. Okay, yeah, motion force you can dump into some damping here, and stiffness here. When you say A11, you can say I22.
That coupling effect, sir.
Yes, you will say, wow, you have I11, I22. There must be I12, I21,
Yes.
right? That is the coupling term, right? Such kind of coupling term, okay. When you write the equation here, right? You have added mass 1 and you have added mass 2. Then that equation is I12 is the second mass motion create a force to the first mass. The coupling term. Coupling term, what's it mean? The buoy is moving, right? And the water surrounding submerged body is also moving. Create a force to this system. Similarly, you have I21, right? Another mass is moving, create a force to the coupled system. Is this clear about added mass? Added mass is a matrix, right? You have two spring mass system, okay, two body system is a matrix. I11, the first motion introduce a force on the first mass, right? I11, and then I12 is this motion create a force here because the water is moving in also. So this is added mass effect. Okay, you may ask, wow, can we ignore that? Yes, in certain condition. Okay, and ballpark number is, if this distance is 2 times, 3 times of this buoy diameter, then you can ignore the coupling. For example, your buoy is 2 meters, another buoy is 6 meters deep, so this coupling will be very, very small. Then in such kind of case, you can draw that way, you can ignore the coupling, right? So if this distance, let us say, compare with this dimension, right, is large, you can ignore the coupling. Physically, you can understanding, okay, this is coupling between, because the water surrounding this buoy, right, is moving, create the water surrounding this tank is moving. If the distance is not enough, then there is no much water moving around this. Then you can ignore the coupling. Okay, so this is radiation force. Radiation force, there are 2 parts. One is added mass term, another is damping term, right? This is I11, this is B11, and this mass moving, it creates such kind of radiation damping. Also, the motion of second body also create radiation damping force here. This is B12, this coupling. Okay. Similarly, if the distance large enough compared with this mass, then this is coupling term disappear. Okay. So then viscous term, and you have first viscosity, second viscosity, like that. And this top part, whether you can ignore or not, you compare with this part, right? The first mass, the radiation damping is relatively large compared with this viscous damping. We ignore that, simplify that. And the second mass is similar order, we don't ignore that. Okay. Now you are also going to have PTO damping, PTO stiffness. Sure, you will have PTO inertia. I didn't write here. You can add another inertial force in between. MPTO times the relative acceleration. Okay, so here you have hydrostatic stiffness. First stiffness, this is proportional to the cross-section area here. Second stiffness, proportional to this smaller cross-section area, right? So then you have excitation force. Excitation force, it depends on how deep that. You understand? And if this decrease to quarter wavelength, depth is quarter wavelength, then the amplitude of water motion is already decreased to 23%, right? So most likely the force on this is small. Okay. However, there's still force here. Okay. Now this is 2-degree freedom vibration system. Now you can solve the 2-degree freedom vibration system. Now the design, what's the design freedom? Design freedom, similar as we learned just now, how to choose the PTO damping, how to choose the PTO stiffness, right? How to choose the PTO inerter and PTO, right? So most likely when we say suboptimal, we can PTO K will be 0, right? And so then you can solve what's the optimal damping. Sure, you can use numeric method to solve this problem, right? Actually, this 2-degree freedom system, you can write a closed form solution too. It's just 2-degree freedom system, right? So one important thing, you say this mass and this mass are important. You just imagine that way. If this mass is infinitely large, it become like that, right? So if this mass become very, very small, what happens? The PTO will not work. The just spring PTO damping force take this mass more together. So as I mentioned that you can optimize the system, right, to write the closed form solution details. You can see this paper, I skip that, okay, and basically spring mass system, mass, damping, stiffness, like that. Now you can get the power. How much power you can get is one period, right, integrate the relative velocity time PTO damping and integrate, right, one period. So similarly as that is omega square relative displacement time C PTO. That is same as single diffraction case. So now as I mentioned that, and this will be function of PTO stiffness, function of PTO damping, right? And you can write closed form solution. So solution all these coefficients like that, function of PTO damping, PTO stiffness, right? You can also write as PTO mass here. Okay, so now you try to say suboptimal, optimal. Suboptimal, you assume the stiffness 0, right? And from this equation, right, you can get the, let me say that way, you can have the damping here, the power equation here, and power equation, and when this PTO stiffness is 0, you just write dP dC PTO equals 0, right? And this is how you solve this suboptimal PTO damping. Okay, and plus this PTO damping in the expression here, you can get the power. This is suboptimal power. Okay. So, and now you can also do the optimal of this expression here, and you can say dP dC PTO will be 0. You can have dP dK stiffness will be 0, right? In that way, you can find the optimal stiffness too, right? And the optimal stiffness you can solve that way. Keep in mind, this optimal stiffness can be negative, right? Sometimes you need to have negative stiffness to tune the system, right? So when it's negative, we can say, okay, we set as 0. We don't want to have negative stiffness. If you have positive stiffness, you put a spring in between, it's easy, right? But if negative stiffness, you have to do active control. Let us say, when you solve that optimal stiffness is 0, is negative, you just set as 0. Okay. So overall, this system performance heavily depend on how nice is mass ratio, second mass and first mass, right? So let us say this is a figure, okay, and the performance, okay, and this line, okay, this x direction's mass ratio is second mass, first mass, and also added mass divided by first mass. This is just one case study. And my impression, this is 8 meters buoy, no, not 8 meters buoy, and 10 meters buoy, and with draft 3.5 meters. That is the simulation result. If you have one body system like that, you can optimize the K, optimize the P. You can have, this is your baseline. If the submerged mass is really small, you cannot get energy out, right? You almost 0 power, right? If submerged mass, you can increase that, then eventually this mass wouldn't move, get close to the single mass case. There's one case in between in which you have maximum power output. The power of two body system is much larger than the single body case. Okay, so And let us see this is result. Okay. Now take a look at this line. The the blue line, this right. So that means, wow, if this mass is small, I still have good power output. Just now I said, okay, if this mass is small, when we should expect 0 power, but now we still have good power output. Actually, I told you what's going on. What's going on now, we have negative stiffness. Therefore, we still can create resonance. Okay, if you constrain the system, you say we cannot have negative stiffness, and this look like this color. Yes, then at the beginning you have small power, and then you can have larger power. About this, you have stiffness is positive, you achieve true, the suboptimal and optimal line converge is same, right? So this line, you get the sense. In conclusion, okay, and the 2-mass system can perform much better than single mass case, right? And another point is the mass ratio is very, very important, right? So a third one is optimal with possibility of negative stiffness, and suboptimal in certain conditions it can be the same, especially when the mass here is larger, then we don't need negative stiffness, right? A third conclusion further, this one is related with damping. Okay, zeta damping is what zeta 2? Zeta 2 damping is submerged mass, the viscous damping, right? I mentioned that first mass viscous damping is not important. Second mass viscous damping is important, because you can say if this case is viscous damping, second mass we totally ignore. And this case, like this line, this group 2 figure, that is viscous damping is 1%. 0.1 is 10%. 0 is 0.1. You have viscous damping 0.1, you can say the power significantly reduced. So what do you want to do? It's so sensitive to the viscous damping of second mass. Then I make a streamline shape. If I have streamline shape for second body, then the viscous damping is small, then we can have big power output. This is why in the system here we have streamline shape, right? So the reason is this is very sensitive to the second damping. Okay, one case you have platform like a flat plate. Flat plate you can still have large added mass, right? Or you understand the plate that have large mass. Physical mass is small, added mass is large. You still can have large mass ratio, right? Because A to 2 is large. However, this flap, that way you have large damping. This type of damping will hurt you significantly. You want to have streamline shape. Okay. This is numerical optimization. You may ask, man, just this optimization, okay, you understand this, like I need to reduce this streamline damping. Why is it better? Why is it better? Okay, let me tell you why it's better. For single mass case, you tune your stiffness mass to match its excitation frequency, right? Now for 2-mass system, you also need to consider the matching frequency. Matching frequency what? Excitation frequency given. You design the system to have 2 difference and 2 natural frequencies, right? This natural frequency can be damped natural frequency, can be undamped natural frequency. Okay, for this mass, 2 mass case, okay, suboptimal, k equals 0. When k equals 0, what happened? Again, let me come here again. Okay, and when this is 0, right, if for undamped natural frequency, the two totally separate. One of the natural frequency will be 0, right, totally separate. Now, we need to consider damped natural frequency. Okay, let us say what's a damped natural frequency. This one, draw this line, okay, damped natural frequency, okay, and it's happen, you say this is best power case happened here, right? The best power case happened here, okay. One natural frequency go with the mass going on, one natural frequency go up, another natural frequency go down. When you have best power output, this happened at the case, the damped natural frequency is exactly the same as the excitation frequency. So, 2 mass system is still matching frequency. The only thing the match is damped natural frequency. Okay, so in this case, when this damped natural frequency happen, what happened here? Let us show the video and take a look at here. Okay, well, man, it's rotate. But rotate, you still can say rotate your head a little bit. Okay, so again, when this buoy move up, this is the motion of tank. The tank move down. Again, say it again. So the physical meaning is when this condition happen, match the frequency, the two bodies move out of phase. When it move out of phase, what happen? You have larger stroke. Therefore, you have more power. Make sense? Okay. And all these are simulation, right? I told students, I don't trust your simulation. Show me experiment. Yes, this is experiment result. Okay. And as I mentioned that you shunt the system as a resistor, you can achieve the damping, right? So, and you change the damping node, look like you change the PTO damping. So this dotted line shows 1 degree freedom system for one particular wave input, right? And you change the damping, the power output will be different, right? You just imagine this way, you damping 0, sure, PTO damping 0, the power output will be 0, right? If PTO damping is infinity, then these two stack together, it wouldn't move. So there's a best PTO damping in which the system will achieve 1.5 or 1.5 watts. Okay. Now the two-body system. Two-body system, similarly, you use different resistor, you use different damping. As you can say, two-body system, then you can have more power than single-body system because out-phase motion, right? So that gives you sense about 2D freedom system, right? So as I say, another figure show I mentioned to you, and when you design the system, right, we designed for single frequency case. How about that result? You design for single frequency case, dominate single frequency, you apply for the broad frequency case to see what the result, right? To say your design makes sense or not, right? This is the result of the case. One case we designed for single frequency, the dominant frequency. Another, we use a numeric method to design for irregular wave frequency. So there are many lines here. I just want to show that the two cases. One is a true optimal for irregular wave, in which we consider PM spectrum. PM spectrum is a well-developed ocean, right? So in this case, you can numerically optimize for all the frequencies, right? That is the true optimal, the black line. Okay. Another case is you optimal for one frequency regular wave, but you apply this parameter you optimized for overall system, right? So this line you get a sense true optimal and also the optimal for single frequency case, right? If you optimize here for this frequency, okay, you can get pretty nice performance, right? So slightly less than true optimal, but still decent. I skip the conclusion. Basically, I want to tell you two-body system, by taking advantage of the dynamics, you can get a much better performance than single body case, right? And the fixed insights is not just numerical optimization, whatever. The fixed insights, you look at the eigenvalue, look into nature frequency, then it happened that at the case, you match the excitation frequency as one of the, I say one of the damped natural frequency, one, because you have two natural frequencies. So I want to show you this result. Okay, that is spectrum. Okay, that is your wave spectrum. This color, right? This is your wave spectrum, right? And this line, black line, shows the optimal or the optimized parameter. This is output power spectrum, right? So in this case, you can have maximum power. This line shows also regular wave suboptimal case. Okay, so and you can use numeric method, and I want to hand over example again, and it's some tools I would like you guys really learn how to do this practice, and you use that for the time domain simulation. And why is time domain simulation? Time domain you can consider regular wave, irregular wave, but frequency domain just one frequency regular wave. Or not equations, but it's two different systems. Everything is look like straightforward, right?